Up next, on the AI side of security, we have Woosun Song from Georgia Tech and Team Atlanta, presenting ATLANTIS, AI-driven threat localization, analysis, and triage intelligence system. Please welcome Woosun to the stage.
Good morning, everyone. I am Woosun from Team Atlanta, the winning team of AICC for this year. Today, I will be talking about what this AICC thing is all about and our unique insights acquired during the competition. So first, I'm going to give you an official introduction to Team Atlanta, the winning team of AICC. We are essentially a merger of four institutions: Georgia Tech, Heist, POSEC, and Samsung Research. We comprise of about 40 to 50 members, and we started working on AIXLT initially on the summer of 2023, so it's been a 2-year effort overall. Thankfully, we got first place, taking home $4 million as a prize. So first, I'm going to begin with what this AICC thing is all about. So AICC, or an acronym for AI Cyber Challenge, is a CTS-style competition where AI-powered systems compete. It was hosted by DARPA and ARPA-H, the joint effort. Previously, DARPA has also boasted a competition called DARPA CGC, or Cyber Grand Challenge for short. Interestingly, this time, they added another objective to patch vulnerabilities instead of just writing exploits. Our team worked on AICC for about 2 years. The competition was initially announced in the summer of 2023, and we made it to the semifinal round, where the top 7 of teams got qualified in the summer of 2024. And this year, in August 2025, we won first place. So this is a vote over team, and as you can see, we have a lot of members. And as you can see in the score breakdown, our team overtook all other teams in all other categories, and subsequently, the aggregate score, we also dominated in aggregate also. So if you see the columns here, there are 3 separate columns for vulnerability score, a vulnerability discovery score, program repaired score, and assessment score. These are the various components of the competition that I will explain in the later slides. So one counts for bias. In short, the competition is a CTS-style challenge for AI systems, not human competitors. However, unlike CTS, whose sole goal is to find vulnerabilities and write an exploit for them, the competition challenges competitors to also focus on alternative aspects, including a task called patch and threat assessment. So in total, we have a total of 3 tasks. First, proof of vulnerability, which is a classical CTF-style exploit writing. And the second one is a patch, where we have to provide a unified disk source code fix for the bugs that we discover. Interestingly, we don't need to submit a proof of vulnerability in order for a patch to be accepted. So it is absolutely possible for a team to submit a bug based on pure postulation without proof. However, this is also very risky, because if the bug turns out to be a false positive, or it breaks the SLA of the organizers, it will result in point deduction. So teams have to game this out and strategically manage their patching strategies. The last category is called SERP assessment, and SERP is a format for describing static analysis results, and it is used in code QL outputs. The goal of this task is to analyze the structured reporting formats and determine if the findings described in these formats are valid or not. And if we manage to submit a valid QOB cache and a SERP assessment, all of these 3 for a single challenge, we get something called a bundle score, which is basically bonus points for doing all homework. And there are 2 types of challenges in the competition. One is called the delta scan, and the other is called a full scan. A full scan is similar to just a regular challenge, where we get the entire code base, and the entire code base is potentially vulnerable. However, for the delta scan challenge, we are given a single diff file, which emulates a single Git commit. And it is guaranteed that that particular diff file introduces a vulnerability. So we can program our agent to focus on those step changes instead of analyzing the entire code base. And so there were 28 related open source projects that were used as the targets. If you imagine CTF challenges, I think like in 2018, there was this trend where people would modify these open source libraries coming from everywhere, and they would introduce like a vulnerability, like I said, dead vulnerability, a buffer overflow or an outbound reads, and they would ask the competitors to exploit these on synthetic vulnerabilities. I think we can consider almost the same. And so we use all sorts of open source software, including SQLite, libxml, curl, and Wireshark. All challenges were structured into a predefined format. Essentially, each challenge is a tar.gz file. And when you untar that file, it untars into a source directory and a bunch of metadata files. One of those metadata files is a file called project.yaml. And it's the most crucial file among the metadata files. It contains the target language, which can either be Java, C, or C++. It contains the repository address. It also contains something called a sanitizer key. Basically, what this is in order to score a proof of vulnerability task, you need to trigger one of these sanitizers. So if for all C and C++ challenges, the address sanitizer was integrated. But for Java, it's a little more tricky because the Java sanitizers are implemented for each bug class, such as SSRN, OS command reduction. So only the ones that were under the author's scope were accepted as vulnerabilities for Java challenges. But for C, another sanitizer patch covers basically all of the bug classes. So for C, it was very generic. And we now have the more important harms file. So to guarantee compilation and reproducibility, each challenge is packaged into a Docker image. And running the bash script build up sh inside the Docker image is guaranteed to produce a lit buzzer and address sanitizer instrumented harness. It can produce multiple harnesses as well. For example, for the NGIX challenge, because NGIX has so many features, there were 3 harnesses, each purpose at causing different targets, including SMTP, mail, and HTTP. And each harness dispatches the input bytes into different functions. In the case of Jenkins, which is a Java-implemented HTTP server, the buzzer provided bytes, the buzzer mutated bytes were stripped apart and deserialized into various HTTP handlers, which each had their own vulnerabilities. So I'm going to introduce some interesting statistics about the competition. The authors added a total of 70 synthetic vulnerabilities to the code base of the aforementioned open source programs, similar to CTF challenges. Some of them were fictitious vulnerabilities, and some of them were based on CVEs. Among the 70 synthetic vulnerabilities, the 7 teams aggregated altogether uncovered 54 of them, or 77%. And among these 70 vulnerabilities, 43 of them were patched in an aggregate sense. One interesting remark that I'd like to make here is that 18 real-world vulnerabilities or 0 days were found during the bioma. Also, the average time to patch the vulnerability was about 45 minutes. Assuming that most of the teams only attempted to patch the vulnerability if they found a valid QOV for that bug, implies that on average it takes about 45 minutes to analyze the bug end to end, which also leads to the question of what's the average cost for uncovering each bug, uncovering and patching each bug. So the cost used end to end is a combined sum of the compute costs and the LLM costs, and if you divide that by the number of bugs, it boiled out to $152. So for each bug, an end-to-end analysis would cost, on average, $152 and 45 minutes. If you think about the traditional substitutes for bug finding systems, which is the hourly of a pen tester or bug bounty programs, is substantially lower cost. So now that I introduced an overview of AICC, let's move on to the next part and take a look at how we structure our system. This is the overall architecture of our system ATLANTIS. Our system, or CRS, Cyber Reasoning System for short, is a Kubernetes cluster deployed on the Azure cloud. Our cluster has two types of nodes. One is a per CRS node, and one is a per CP node. A CRS is an acronym for a Cyber Reasoning System, and it's just a fancy word for this AI system. And a CP is an acronym for Challenge Project, and that just means a single source code subject to analysis. The per CRS node is a persistent node that is alive throughout the entire competition, and it is responsible for dispatching tasks and creating the per CP nodes every time it receives a new task. The per CP nodes are only alive. These are ephemeral nodes that are only alive during the analysis of a single challenge project. And this is where all the import subs reside. Among the per CP nodes, the serif, patch, and the bug finding modules are the modules that actually use the alerts. And the CP manager module, which is responsible for dispatching tasks internally, do not use LNs at all. Within the per CRS node, we deployed a right concurrency to streamline the management of budget and bug access. Today, due to time constraints, I will only focus on the bug finding modules. Our key design for the bug finding modules was diversity and complementary specialization, where every module takes a different approach. First, there are two advantages to this. Firstly, each system is an expert on its own domain, allowing us to uncover a diversity of bugs. Second, due to the independence and the diversity of the approaches, our system is robust against varying inputs, allowing each module to act as a backup to one another. And so, our design decision was also substantiated by a bug finding results, where each bug finding submodule, multi-line C and Java, found its own unique bugs. We can see this in the per module bug finding results, where each bug finding module discovered its own unique set of vulnerabilities post-deduplication. Today, I'm going to take a deep dive into the multi-line module, which I put in the most amount of effort. The key intuition of the multi-line team was to improve buzzing. To give you a real quick background, buzzing comprises 4 steps: seed scheduling, input generation, input evaluation, and state updates. The most popular way of scheduling seeds at the moment is coverage-guided and directed buzzing, and people have been using this for 10 years. For input generation, there are numerous traditional methods, but primarily it involves compiled execution, dictionary-based input generation, grammar-based input generation, and hierarchy-specific buzzing. However, these approaches have their own limitations. One of them is that they lack multi-language support. And the second one is, it often requires time-consuming manual analyses. For example, when we consider directed buzzing, we have to choose what target lines to direct the buzz towards. In terms of dictionary-based buzzing or grammar-based buzzing, when constructing the grammar set or the dictionary set, there is a substantial amount of manual effort. Thus, our intuition was to fully automate these processes using LLMs. As an alias for ATLANTIS multilan, we use the term UniAFL, which is an acronym for Universal AFL. This name was appointed to describe a system that can hunt bugs in a language agnostic sense to some extent. Again, we borrowed the design principle of diversification. This time, we diversified the components inside the input generator based on LLM usage. Looking back, I think this design decision wasn't necessary, and this was mostly stemming from the fact that LLM credits were heavily limited in the initial phase of the competition. We were allocated about $400 per challenge, which is very short, and therefore we needed to save budget, and we needed to isolate the components that heavily use the LLM so that they don't interfere with other components. But looking back, we didn't have this limitation in the final round. So I think one aspect that we could improve on is to aggressively use LLMs. In terms of diversification, among the input generators, the given buzzer and the concurrent executor does not use LLMs at all. And on the other hand, our system of agents, which we call MLLA, comprising of 5 different agents in the curvable box that you can see in the middle, are the other end, intensively using LLMs to their fullest extent. And in the middle, there are these miscellaneous modules such as the dictionary-based mutator and the grammar-based mutator, which uses LLMs moderately. So today I will focus on the ensemble of light agents that use LLMs to their fullest extent. The goal of these agents is, when given a source code, they need to find concrete inputs that are capable of crashing the source code. And to do this, we do it in a 2-step fashion. We first hypothesize by employing interprocedural analysis and synthesizing potential bug hypotheses, which we call bits, or bug-inducing things. And then using these bits, we actually attempt to generate concrete inputs that prove that these bits are valid. The structure of a bit comprises key conditions and a bucket location. So if you think about triggering a bug, you must first navigate into the vulnerable function, and then you must pass all the key constraints up to the vulnerable state, and you must pass malicious input to a state that actually triggers the bug. The code snippet in the slide is an example from Apache Commons Compress. And the vulnerability here is an OS process injection OS system command injection vulnerability, where name is provided to the constructor of process builder, potentially causing arbitrary command injection. In this case, we have to manage 2 conditions. First, we need to navigate through all the flags that lead up to the construction of process loader, and we also need to set fname in a way that makes it behave in a malicious manner. So a key insight for obtaining bits is to focus on only the important functions instead of looking at all the functions. We have 2 criteria for what constitutes an important function. First, that the function is reachable from the buzzing harness, and second, that the function is included in the diff if the challenge is a diff type challenge. And the second phase, which should actually construct a concrete inputs on the list, is the more interesting part. So we had 2 intuitions for the concrete input synthesis part. So the first intuition is that instead of making LLMs generate the seed bytes directly, instead we should make it by a script that generates the seeds instead. And we also employed 3 different strategies and aggregated the results for better probability. The 3 strategies are: first, creating a single highly targeted payload; second, creating multiple targeted payloads with breadth; and third, creating use case strategies for better depth. So to introduce the first one, this is the most rudimentary version of the 3 strategies. The code snippet on the left depicts a Python script whose objective is to synthesize the malicious gzip payload that contains a file name spelled JEZZE. JEZZE is just a string that triggers an OS command injection satisfies crash. This approach, compared to the approach of using LLMs to directly synthesize input bytes, has several advantages. First, it makes the synthesization process less error prone. Programmatic generation of inputs are not susceptible to these dumb errors such as incorrect onsets or lengths. And second, by reviewing the script, we can get a glimpse of how the LLM is understanding the target program, which is extremely crucial for incrementally improving our system. And from the perspective of the callback, this strategy can be described as kind of one-shot, an intricate path from start to beginning, all the way up to the bug function. However, this approach is not appropriate for complicated compounds that are beyond the LLM's capabilities to reason. The two other strategies that I will explain now will compensate for this limitation. And so the second strategy is to construct a generator, which is a function that creates probabilistic payloads based on program analysis results. The second strategy is essentially to construct multiple payloads targeting many functions at breadth instead of depth. The example on the left demonstrates such a case. The script generates a random XML that includes various entity types, aiming to reach different handlers in the parse-through function. And the final strategy is to create mutation search, which is helpful for depth and surgical precision. The example shown on the left is an exit file mutator, which attempts to corrupt various skills of an already valid exit file. This helps reach the buggy point within the deep already reached function. The generation of these scripts undergoes iterative refinement based on coverage feedback. First, we copy LLM to write these scripts. And second, after running the scripts, we provide the LLM with the source level coverage of the inputs that it generated. And based on the source level coverage, the LLM reflects on its own input and script and tries to improve. So in this case, the LLM has successfully identified that although it has reached the vulnerable function from base 85, it realized that it didn't provide sufficient length to trigger a buffer overflow vulnerability, and therefore it must adjust the script reporting. And we repeat this process of output to a fixed number or till the script results in patch. And we're also going to discuss some prompt engineering strategies. So similar to other prompts and prompt engineering best practices, we concretely describe the role, the variable, the workflow, the context information, as well as an output example in the system prompt. And then when getting the source code, we use these best practices from previous literature, including Rust Assistant and Anthropic Solidites. Also, because internet access was strictly prohibited during the competition, we had to add the sanitizer-specific domain knowledge for the prompts, especially for Java. For instance, the sanitizer for Java packages required providing these very special string literals to trigger the sanitizer. One of them is the JAZZE string that I mentioned previously. And adding this information greatly improved the accuracy of our generators and indicators by over 50%, implying that these models didn't have prior knowledge of these sanitizers. And now we're going to talk about the bug finding results very briefly. And so a very interesting point is that for each model, even within the same model family or similar timelines, they exhibit different properties. This was exacerbated, especially for Java harnesses, because we could classify bugs into different, very distinct categories, and they exhibited different properties in each of the categories. So in terms of model differences, we could obviously notice that some models perform better for server-side request forgery, and Anthropic's models don't really know about server-side request forgery. But on the other hand, even within the same model, which is expected to have been trained from a similar dataset, they exhibit drastically different performances. And lastly, sometimes newer models which are advertised to be more advanced lack knowledge. Especially, you can see this from the file path traversal example, where Claude 4 was released later than Gemini and OpenAI's model here, but it performed much worse. And it is also possible that each model requires a specific prompt to perform in the best way. And so our verdict of what model to use turned out to be Claude 4, because even though in all of these minor limitations, they turned out to be the most efficient and accurate overall. And we also found 4 zero-day vulnerabilities during the semifinal and the final rounds. And I'm going to introduce you one of them. This is a classical use-after-free vulnerability caused by a specific callback that doesn't initialize this D data pointer to null. So what happens here is if we create a table indexed by this LSM1 module, it is a virtual cursor table. And if we create two entries, key 0 with a value of length 6 and another key 1 with a value of length 7, the Z data field will be reallocated in the second iteration and cause a double free. We also generated a successful confirmness, which is to just move the initialization outside of its loop. And I think although the bug root cause is very simple, the payload to trigger this bug is extremely complicated, and I'm very confident that existing buzzers would not have been able to trigger this bug due to the complexity of the SQL query that would have to be inputted to the parties. And therefore, I think this bug is something this bug was also something that only RT could find. So I believe that this definitely demonstrates an advancement in bug finding due to AI. And so we're going to talk about next steps. A lot of these foundational model companies have been heavily invested in AI, apply AI to security. All three major foundational model companies are heavily invested in developing their own AI agents, including OpenAI's Arvar and Google DeepMind's CodeMender. Also, recently, Anthropic decided to invest $1 million to Pico CTF to expedite their development for Red Team AI. It's kind of paradoxical also because although AI can help security researchers and white hat researchers find more vulnerabilities, it is also possible that it boosts attacker productivity. If we come circle back to the original AIXT results, the average time and budget for finding and analyzing a bug end-to-end was $152.45, which means that attackers can also now run their VOLOPs at scale, in a substantially efficient and cheaper manner. So I think applying AI to security is a double-edged sword, where both security researchers and attackers get a substantial advantage. And for me personally, I'll be working on a new project where we are creating an ATLANTIS adjacent system targeted towards the Web3 ecosystem. I decided to focus specifically on this domain for two reasons. So first, I believe that security in this space is insufficient compared to the rapid growth of the Web3 space, and therefore I found this problem really important. And second, there are unique challenges that make this space interesting. So I'm part of a 4-person team with advisory from the team at lead, Professor Kei-Soo Kim. And we have outstanding track records in all sorts of awards, including AIXC, DevCon CTF, Home2Own, IOI, ICKC, and Paradigm CTF. Furthermore, we have a robust network within this specific space, so I believe that I can provide a strong argument for deploying capital to us. So please give me contact. Thank you, and this is the end of our presentation. If you have any questions, feel free to ask.
Thank you, Woosun, for the fascinating session on AI-powered threat analysis. It's amazing to see how automation and machine learning are reshaping incident response. So do we have any questions? Please feel free to raise your hand.
Did you run into any problems with models rejecting your prompts? For example, I found ChatGPT very happy to tell me where a bug is, but not write a proof of concept for it.
So you're talking about safeguards, right? We did run into this problems initially when we prompted the LLM to directly create exploits, but we unintentionally kind of circumvented that by, if you see in our strategy, we asked the LLM to write generators and mutators for a buzzer instead of writing an exploit directly. So we inadvertently bypassed it.
Do we have more questions?
Hey, did you have any issues with ingesting code coverage? Because I think it would be quite a lot of tokens if you tried to put it all into the LLM.
Yes, that's an excellent question. So I did put that in the slides, but I skipped it because of time constraints. How we did it is we first provide a list of the unique function names that were covered by the coverage, and then we ask the LLM which functions you want to look into. And we choose 3 functions of them.
Thanks.
One last question, please.
Did you have any issues with context being too large and models hallucinating?
Initially, we did. I think there are 2 problems. The first one is just the context window diminishing. I think the context window diminishing is more an engineered problem. And I think the bigger problem is the performance of the LLM deteriorating if the context window is saturated. We didn't really... Thinking about it, I think those are probably identical problems. We didn't really run into those problems because the way we use our LLMs, we didn't shove the entire code base into the context window analysis to find bugs. Instead, we provided a very small portion in a controlled manner as the input. So I think I can say that we carefully engineered to not saturate the context window. I'm not sure if this is what you are asking. Is that sufficient?
Yes, thank you.
Okay.
Okay, thank you, Woosun, for the session, and let's give him a huge round of applause.